Good evening, guys. So we will start in next 5 minutes. We'll start sharply at 6:05. Okay. Hello, hi, namaskar. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Mumbai, and here we are learning advanced thermodynamics and molecular simulation. So this is our week 9 of the live interaction session where we discuss the questions, various assignment problems, and the session that we have covered, or the topics that we have covered in the recorded lecture. So let's start with the interesting session. So here we are learning advanced thermodynamics, and I am repeatedly saying that we are developing the molecular level understanding of the undergraduate thermodynamics that we have studied earlier, right? So we are developing a understanding molecular understanding. Earlier in our undergraduate studies, we used to talk about the systems at centimeter to meter length scale, right? And we used to measure any observation of a particular system which is in centimeter scale. For example, I have a bottle in which I have water. It has a dimension of some centimeters, 10 centimeter to 100 centimeter, right? And then As soon as we add some dye in that water and we see how it is evolving, and we also study equilibrium properties, right? So there the time is in seconds or minutes. So this is the time scale. So length and the time scale, correct? So there is a very famous diagram which you can refer to on internet, right? So they talk about time and versus length scale, where you'll find the system that we studied, water in a bottle containing dye, something like that. So it happens at this centimeter scale, and then there is time that has been recorded or measured in in seconds. When I go deeper here, so atoms and molecules and electrons will come, right? So this is where we are at atomic scale. Atomic scale, that means we consider that atoms to exist, right? We can go again below that, and we can have electron as our fundamental particle, right? So depending on the fundamental particle of the system, we can go at lower scales. So in this atomic scale, we have dimensions in angstrom. Dimensions in angstrom, and the time over which we measure, because these fluctuations and what and all the things that are happening in the system, they occurs at femtoseconds to picoseconds time scale, right? So time is in nanosecond, I could write picosecond, right? So at this small time scale, these events happen. For example, I have a molecule like this. For example, this molecule where I have HOO. So this is my water, and I know it has a bond length which vibrates, right? So see, this bond vibrates around a mean position, right, which is fluctuating bond. This angle is there, right? So all these events that are happening, no, this happens at nanosecond to picosecond or femtosecond scale. Over the period, you see how the molecules and system is evolving, and when we do these sort of things, we go up to nanoscale, right? We start with femtosecond time step, and we go up to nanosecond time scale, right? And nowadays, because of the supercomputing facilities that is available, the researchers are studying the systems up to microseconds time scale. There are some events that happens over microscale. For example, crystallization. If you do not do these sort of things, or if you do not do the simulations, or if you do not study that system up to that much of time scale, then you are going to miss some of the events that are important, and they are not able to be captured in molecular simulations, right? So that's how we are going into the molecular details, where time and the length scales are different than the continuum scale or the classical scale that we generally study. And based on this, then, just like we used to define open system, closed system, here also we define multiple types of ensembles. So this is a recap of what we have studied till date, and this is really very helpful, right, to solve the assignment problems, right? So, so we studied multiple ensembles, for example, NVT ensembles, NPT ensemble, and so on. So what are these? These are my controlled variables, and depending on these control variables, we can have systems, for example, open system, closed system, and then there are systems which are isolated systems, and so on. We can study all these things using molecular simulations, right? So we have defined ensemble, and for that particular ensemble, if something has to happen in that ensemble, there is something called as free energy, which will tell whether the process is spontaneous, will it happen or not. So there we define something called as free energy for each ensemble. Depending on the system that is under consideration, you define what and all are the controlling variables, what are controlling open system, closed system, or isolated system. And for that particular systems, we have defined a free energy, which will tell you feasibility of the process. Connect feasibility of the process that is happening. Right, we define the ensembles. So what happens when you go at molecular scale? You have, for example, just like I had shown you, this is my water. Similarly, there will be multiple water molecules which will be there. What I am going to do here is I am going to evolve the system in time, evolve the system in time, and take multiple snapshots. Take multiple snapshots. And in each of these snapshot, I will see the molecule is changing its position, and how this position will be obtained based on the forces that are acting between the particles, and forces will again give rise to something we refer to as here in velocities. So particles will have positions, they have velocities, right? In a particular snapshot, the particle will have some position and there are some associated velocities. These velocities and the positions will be used to get new positions and the velocities. New positions and the velocities can be, right? So these positions and velocities are there for each particle in system. What do I mean by particle? This is atom. So each atom, for example, I have 1000 water molecules. Each water has 3 atoms, so obviously into 3, right? These many atoms will be there. 3000 atoms. 3000 atoms will be there, and these 3000 atoms will have positions in space. Each atom is a point particle. It has some diameter, right? It has some diameter. So these particles will have positions x, y, and z in space. So this is there for each particle. So how many of these will be there? So let's say if I am having n particles, then I will be having 3n positions. 3n positions. So positions will be n, which will be defined using x, y, and z. So this 3n variables which are there, which are varying, that describes the position, that tells you the position, right? XYZ of a particular particle in a space is there. It is keep on changing, right? So for one particle, XYZ is there. Three similarly for n particles, there will be 3n coordinates which will define the position of those n particles. So there will be 3 n coordinates which will define position of n particles. And particles, right? Any doubts till this point? Now the question to you is, in that particular state these particles will have some velocity which will give you the positions in new microstate, new snapshot. So how many velocities will be there? How many velocities will be there? Please let me know. I have n particles. I have n particles and they will be having velocities. How many variables are more than the xyz that we have defined will be there? So there will be again, for these n particles there will be resultant total n velocities will be there, which has components in x, y and z, because velocity is also a vector along with the position, right? So there will be three velocities, vx, vy, vz, for each particle. So for n particles there will be 6, there will be 3 n velocity variables will be there, right? Whose position is, whose values are basically changing over the time, right? The velocities are changing over the time. So total how many are there? So total there will be 6 n variables. How many? 6 n variables which will vary with respect to time. These many variables which will vary with respect to time. For example, if I am having only x as a function of t, or I will write y as a function of t. How do I plot this? If I want to plot this, I'll be having y here, I'll be having t that represents time. This time is changing, and along with the time this y variable is changing, right? Right, so this variable ka value is changing. So how many dimensions it has? It is 2D plot, right? If I consider time as something which is by default understood, then it is one variable that is varying with respect to time. So how many variables? One variable. Here I am writing, I have three, four, five. I don't know how does, how much, how will it look like, but then this is having x, y, z, vx, vy, vz, and multiple x's will be there, right? and this all will vary with respect to time, right? So there will be multiple variables, and how many those variables will be? 6n variables which will be varying with respect to time. So it is 6n dimensional space, and time is also included there. So this is, or I could say 6n plus 1, both are same. Here I consider time as explicit definition, but here you can see no time definition is explicit, it is already included. So these many variables, so this is 6n dimensional space, right? It is 6n dimensional space, correct? These many variables are varying with respect to time. How did I get that? I said, okay, I have some molecules are there in the system. How do we start? We said, okay, there are these many water molecules in the system. Each water has three atoms, right? And one atom can be defined in space using its position vector with three coordinates x, y, and z. Each of this atom will have velocity, that is resultant velocity, which could be in any direction, and it has individual components Vx, Vy, and Vz. So for one particle, you just substitute value of n here. So n is equals to 1. I'll get 6 variables which are varying with respect to time. So if I'm having n particles, that means 6n variables are varying. 6n variables are varying, right? That means 6n variables are varying with respect to time. So this is 6n dimensional space, and this is referred to as phase space. This is called as phase space, where we have positions and the momenta is varying. So I'll write over here, just like I will be having pi, that is my momenta, and this is my ky, that is my positions, and this is my phase space where the particle is evolving, and its velocity and the position is changing over the time. Its position and velocity is changing over the time. So you can see there are multiple values. The particle is moving, or particles in system are moving, and as they move their position and velocity changes. This will keep track of. So we will see this variation of position and velocity, where each point will have 6n values. So this is referred to as phase space, and then phase space has information about positions and velocities. Correct? Now for a particular state which represents a microstate. So each point in this space represents what? A snapshot, or in technical language we call it as micro state. Each point represents a micro state, right? And how to get the energy of the system? Based on this microstate, we'll use some formula to get the energy, and that energy will give rise to the probability density of that particular state, that I'm writing as rho, which is equals to exponential minus beta ei. So for atom is this, and for system which has n atoms, I'll be having, say for it, this for system which is equals to I is equals to 1 to n exponential beta ei, exponential beta ei, which will tell you the probability density. Probability density, so it gives you the value. That value represents, okay, for a system to exist in that particular state, what is the probability density, right? And here n is number of atoms, and this is again for a particular, snapshot. Similarly, there will be n number of snapshots will be there, over which I need to calculate this value. So there will be one more summation. Large number of snapshots can be taken out. This is for a system. Which will give you a correct value than previous, right? Then we discussed about something called as Liouville's theorem, which tells you that the volume of the space is incompressible. So we take a very small volume fraction here, right? The small volume fraction will look like this, right? Each point represents a microstate, and if I know number of microstate divided by volume, it will give the density of phase space. Density of the phase space, which is not changing, it is incompressible. Incompressible. What does this mean? The phase space is incompressible, that we have understood using Liouville's theorem, which says that, okay, phase space is incompressible. Meaning is that there is each and every point in the phase space, there is some point, there is a point. If a microstate go out of that particular chosen small volume, another state will come at that position, right? So for example, I am telling you, I have position is equals to 1 and Vx is equals to 1. If the velocity changes, then I'll go to x is equals to some value, let's say 10, and Vx is equal to some new value, that is again 10. So as soon as the particle is leaving this phase space, another particle will come and that will occupy this. That means phase space is never having voids, it is a continuous phase, where if the system leaves a point, if another system or microstate will come at that point. So this is incompressible. It is incompressible. That is basically given by Lewis theorem. That is, at any given point there will be always a microstate. There will always be a microstate. That means if a particular microstate leaves a particular point in the phase space, another system will come and occupy that location. That means those values will match to previous snapshot values that has already gone through the state to a new state. This is how it is. So I told you about density, and density is, again, you can see in the equation, is a function of energy. The bigger question that we have in these is how to get the energy of the system. How to get the energy of the system. We have studied that in class. Please let me know how to do that. How to get the energy? That is the question. We know that the probability density of that particular phase space depends on the energy, right? It depends on energy. So the question is how to get the energy. So we know that the density is a function of energy. So how to get the energy? We know from our basics that we have studied how to get energy of two particles. How to get energy of a system. What a system is composed of? The system has particles or molecules. The system has particles or molecules, right? These particles or molecules, right, will move. And for example, I have one particle at this location, other particle at this location. How to get the energy between these two particles? Similarly, I'll calculate energy between this particle and this particle, this particle and this particle, and so on, and I'll get the energy of system. So energy of the system is the summation of energy between particles, right? I can write about energy between molecules. Again, molecules are composed of what? Particles, and particles are referred to as atom in this part, right? So atoms will be there. How to get the energy between two atoms? For example, this and this. We know from our scientific learning to date, let's say there is some q minus charge over here and q plus charge is over here. The energy between this is given as u is equals to k q1 q2 upon r, right? It is what it is, q1 q2 upon r. This is what is the interaction refers to. So you just substitute the values of charge, right? You substitute the value of r, which is the distance between particles. So upon substituting the values of charges and the r, we can get the energy between two particles. We will do it for each and every particle in the system, right? With a caution that interaction energy between 1 and 2 is equals to 2 and 1. So there should not be double counting. So whatever the normal calculations we do, we can do that in the same way, and we just need to divide by 2. Approximately it will give in the same value, right? Some values will be there because self interactions are not there, but then okay, overall I can say you have to sum it over all the particles in the system to get the energy. Now I'm just saying, okay, it is having positive charge or negative charge. I don't know what is its magnitude. It is exactly positive that value or particular value I'm referring to. It is not. It will give me a trend. For example, if I calculate interaction energy using this, if I plot between two oppositely charged atoms, so what is the value? Q1 is equals to plus 1, Q2 is equals to plus minus 1. Then interaction energy will look like this. And it will keep on decrease. You just need to plot this. You can easily do that. It is more or less 1 by R. Secondly, if I consider positive, again positive, then there will be a repulsion like this. Correct? If both are negative, again the energy will look like this, the black one. If both are negative values, right? Both are negative values. So what does it give? It gives you what will happen to the interaction energy qualitatively, or it will give you something called as trend. If there are positive charge atom or negative charge atoms, that means similar charges versus different charges, What does it give? It gives a trend whether there will be attraction, I mean to say energy is equals to negative, and or there is repulsion, positive. So this is something called as physics based model, and these are referred to as generic model to get interaction energy E, referred to as generic model. But if I say I have positive charge as Na and negative charge as Cl, this is specific. Then I also need to define what is the diameter and various other properties of these atoms, right? So in that case, particular model, and this is called as molecular force field, which is chemistry based. It will give some charges which are different for KCl, K2, or K2CO3, or some other property, what and all. So that will be specific to that particular ion, right? So it is chemistry based. We cannot change that value. We cannot say that Na plus is also positive ions and K plus is also positive ion, so both will behave same. No, in that case we need to go particularly. So again, example, K plus, and then there is Na plus. We know q1 is equals to positive, we can take q2 and all, so we can it will give us a trend how energy or some other property is changing with respect to a charge, positive charge or negative charge, plus one charge. But then if I say okay, it has some different diameter, the Na has some different diameter, and depending on these properties, some properties will be different. Some properties will be different. And what do I mean by diameter of the particle? Just like I said now, it refers to the size of electron cloud. So obviously Cl minus will have higher diameter or size than Na plus ion, than the Na plus ion. Correct? So here I am going into particular chemistry. So these are specific model called as molecular force fields, right? Molecular force field. So there are multiple ways in which I can get the energy. So this I talked about the energy which depends on the charge, so it is electrostatic energy, but total interaction has some the other parts also. For example, total energy will be equal to E bonded energy plus non-bonded energy. Bonded will be present between the bonded atoms, and non-bonded will be present between non-bonded or bonded atoms. So this is there. It has angle, bond, and dihedral. Dihedral is meant what we'll look after, and non-bonded. So it is electrostatic interaction, that is ES, or it may be van der Waals interactions, or yeah, van der Waals interactions, which we model using LJ. Here we model using Coulombic potential. So there is a particular interaction that is happening between atom, right? It could be electrostatic or van der Waals, that you do not need to worry about. But then there is something that is helping us to model this. Energy is there, we know, but how to model, how to get the value, that is called as model. So that given q2 upon rk, right, that is the model given by Coulomb, and that's why it is called as Coulombic model. Similarly, if we calculate dispersion interaction, that van der Waals interactions, we have something called as LJ model. We can have multiple ways in which we can estimate, right? So depending on the type of interactions, we can have hard sphere model, we can have square well potential, or we can have LJ potential. So what does this each of is referring to? hard sphere model, that means there will be some interaction energy E is equals to 0 up to this distance, and here it is shooting out to infinity. So at r is equals to, this is my r and this is my diameter of the particle. If one particle is present here at origin, other particle is present somewhere at distance r, if r is equal to sigma, then energy is infinity. If r is greater than sigma, then energy is equal to 0. This sort of model is called as hard sphere model. But then there is no interaction up to certain distance, and after certain distance there is some infinite interactions, right? This is what is happening, right? We also see there is discontinuity, and when we look after in the literature, we will also going to know that there is, here it is saying that there is only repulsion between the particle, attraction is not that all there, and the energy for the attraction is zero, that means no attraction. But in real life there is attraction between atoms, that we know, right? And that's why we need to go with some other model that will accurately represent that part. So then we go with something called a squirrel potential, like this. What does this tell? This tells you up to certain distance, up to certain distance there is no interaction. Then there is suddenly interaction which is equals to epsilon value, this value well, which is called as potential well. And then again when it goes to sigma, there is repulsion. This sort of potential called as square well potential. Again here there are a lot of discontinuities, and that's why, can we again now convert it into some potential like this, which is a continuous? Again advantages, we are allowing that there is attraction between particle up to certain distance. You can see the molecules allow the penetrations, and this molecule is there. If it touches this molecule, there has to be infinite value of energy, right? That's what the hard sphere model told. But now we are saying, oh no, 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 molecules can penetrate up to certain distance. So this is what is, as soon as it reaches higher value or more penetration, what will happen? The energy will shoot up. That will be taken care by the potential. Third advantage of it will be, we know that ultimately using energy we are going to calculate something called as force. Force is equals to minus of du by dr. So u is my interaction energy. We take the derivative, we are going to get the force. So this u, that is what is giving you the which is called as potential, that gives you the interaction energy between particle. Interaction energy between particle, right, has to be a continuous function to get the derivative. That's why we go with something called as Lj potential, which has a formula ulj is equals to 4 epsilon like this. This tells you what is the strength of attraction. Again epsilon, this well depth. Sigma is the diameter of the particle, atom, diameter of atom, right? And r is the distance. Depending on the distance, we can calculate what is the interaction energy. Now we have to tune the value of these parameters. What is the epsilon, that is interaction strength between atom A and atom B, and the value of sigma, that will tell you where up to what distance the penetration of two atoms is possible. Correct? Penetration of two atoms is possible. So diameter and these things. Now this we need to tune and match with the properties of the system. For example, I have Fe2O3. So there will be atoms of Fe and oxygen. I need to I need to find out the value of sigma and epsilon for Fe and oxygen such that it will reproduce experimental properties like density. We know what is the density of Fe2O3 crystal. We need to validate it something called as surface energy, which is the energy required to break the system. Upon breaking, we will get what is the energy. We need to validate it. We need to find out the value of all A, B, C, which are lattice constants, alpha, beta, gamma. These are called as lattice constants. So these values should match. So we need to tune the value of sigma and epsilon in this equation or charges, that is Q present on Fe and oxygen, so that they should match these properties. And once they are matching the property, we say okay, now my parameters are representing my system. I can do lot of any other calculations to see the interactions at molecular length and time scale, right? Molecular length and time scale. Then we talked about Monte Carlo scheme. Now the question was okay, using this interaction energy we get the force. That force can be used to get the next position and the velocity. So here what I'm doing, I'm moving in time. Earlier I had x and v as the position and velocity. Yeah, I go in time, I'll get x2 and v2 for each particle, right? And this is evolving. So what I'm doing, I'm following time, right? And what does each state represent? It represents a point in a phase space, just like what I have drawn over here. I'm moving in space, right? I'm moving in space and I'm sampling this space. So if I draw here correctly, this is my space where I am evolving the system. So I can go and follow the time, and this method is called as MD, where we solve Newton's equation of motion. On the other hand, if I do not follow the time and randomly go from system A to system somewhere D, and then D2 coming back to B, and then coming back to going to Z or something like that, right? So in that way also randomly I can sample up in multiple steps. So I can sample with respect to time, and I can also sample with respect to random and going into its state and checking whether that state is possible or not. So this method is called as Monte Carlo method. We'll discuss about it, right? So this is Monte Carlo method. Monte Carlo method. So we have molecular dynamics as a method which follows the time, which is the deterministic way, right? Which will give you the true dynamics. The question is there in the assignment, because it is moving, it is going with respect to time. Whereas in Monte Carlo, it is random, and the objective is only to sample the phase space, right? So now we'll just solve some of the questions which are there in the assignment. The first question is, force field contain the information about what? I told you it is a combination of equations, right? This is what is force field, where we have equation and we need to find out the values of parameters, right? So it is a combination of equation and parameter. What does that give? That gives you something called as energy. So it will give you energy. That means it will also give you the forces. So it is a interact it gives the interaction energy between the atoms of the system as a function of time. No, this is not the case. It gives you the interaction energy between atoms as a function of separation distance, just like I had drawn 4 epsilon ulj is equals to 4 epsilon sigma by r raised to the power 12 minus of sigma by r raised to the power 6, right? So which gives you as a function of separation, right? Separation distance, and then it will also gives you force as a function of separation distance, right? So these two options, I would say, first of all, correct answer is option 4. But instead of interaction energy, if the force would have been written, that is also correct, as a function of separation, and not as a function of time, not as a function of momentum. Correct? So option D is correct. Option D is correct. The next question is soft sphere model, right? So we have studied hard sphere model, soft sphere model. Hard sphere model is something that tells you, okay, energy is no, energy is not present between particles up to certain distance, and then crossing certain distance, it gives you certain infinite value, right? So that means either there is interaction or there is no interaction. Interaction or no interaction. Right, so we have gone to soft sphere model, which allows you, okay, first of all, that we are allowing the overlapping, some overlapping between the particles is permitted. There is no discontinuity in the energy. We are not saying it is a continuous function of the r. That means ulj, just like what we draw, this will look like this. So ulj will be there. It's a continuous function of distance of separation, and it gives you easiness while solving the equation. That means numerical difficulties are not there. So these three options are correct. These three options are correct. Then there is question number 3, Lewis theorem. Again, this also we discussed, right, while discussing the previous class what we have studied, right? So we studied Lewis theorem says that the phase space is a hypothetical fluid which is incompressible. Why incompressible? Because if I take, this is my phase space which is evolving, I take a very small volume, and in this small volume, any microstate that leaves, another microstate will come and occupy that position. That means it is not having any voids. It is always occupied, and it is incompressible. That means it is incompressible. That is about Lewis theorem. Question number 4. This also we studied. So what is this? True dynamics can be captured using molecular dynamics. Just now we saw that it calculates the position and velocity, or gives you the position and velocities of particles with respect to time. So we are following the time, and that's why we see dynamics. So true dynamics is possible if you randomly choose points between phase space and then see whether that point is possible or not. Some of the points will be possible, some will not be. Some region will be more more that needs to be sampled, right? And some is not, right? That's why molecular dynamics is something that calculates with respect to time. So it is true dynamic. It samples the true dynamics. Question number 5. Monte Carlo method. Monte Carlo is a integration method, right? To integrate the values, right? So we need to get the density as a function of e to the power minus beta e. So you need to sample these points. What all energy points are possible? So it's a method of integration. Method of integration. Weighing function is used in importance sampling because, as I said, I have a phase space, and I told you there will be some region which is of importance. Some of the region will be having very high energy, and as I told you, there is some distribution called as Boltzmann distribution of energy, which we studied, right? Number of particles in higher orbital divided by number of particles in lower orbital is equals to exponential, some formula was there, and it was again energy related. If energy is higher, if the energy is higher, ei minus ej, like that. So if the energy is higher, that means the probability of existing in that particular state is not feasible, right? So what happens, there will be some region which needs to be sampled higher than the other region, right? So that's why we are associating a probability with a particular microstate, right? So this is what is referred to as weighting function, that is used in importance sampling, because its value is higher in regions of higher probability density. So weighting function should be such that its value is higher in the region where there is higher probability. So here it should be having higher probability so that we can sample it more than the region which is less probable. Now number of dimensions in the transition matrix in a Monte Carlo simulation. Number of dimensions, as you know, in Monte Carlo simulations what we do, we are standing at a particular state A and we are moving to particular state or some other state which is equilibrium state, right? Which is equilibrium state. Some Z state which is in equilibrium, which is an equilibration, which is the equilibrium state. We have to go from state A to state Z. Now the state Z is something which is more probable than state A. We have to go to that state. We can go in one step at a time in time by following the time, just like what we do in MT, right? A to B, B to C, C to D, and so on, right? But in Monte Carlo, what we do, we directly go to some X state, we directly go to some Y state, or P or Q or B's, what and all. It is random, right? And we just see what is the probability to exist in that particular state. That probability is referred to as pi to exist in that particular. It is not pi, it is row of existing in particular M state. And I'm going from M state to N state, so there is some transition that is associated. So that transition probability is Mn, which is equals to transition probability of staying in new state into the density. This is M, this is N, and M, right? So these are the density to exist in a particular state, and this is my transition probability that is associated, right? So here we can go from a particular state M to any state N. So how many possibilities are there? There are infinite possibilities, right? So that means we are going from a particular microstate A to Z, particular microstate A to any infinite dimensional microstate. So how many microstates are possible? Infinite. So we can go to any. So it is ideally referred to as, or we can consider as the total number of microstates of that particular system. But we know that we cannot sample all the microstates, and that's where, if this is my phase space, we'll consider some important zone. This is a chosen, this is a chosen state space which we are trying to sample, because we cannot sample entire phase space. and that's why we can go to any state within that chosen state space. So option B is correct. Number of states in the chosen state space, right? Not all the micro states. We can go to that, but then it is very difficult to sample all these points. You have to do simulation for large number of steps, large number of steps to sample it completely. That's why we chose a small sub state space and we sample it, right? So this is answer. Then stationary solution in Monte Carlo simulation is perform over state space repertoire. Stationary solution means I know if there is any property, that any property, for example density, is a function of microstates and it's also a function of time. So it is stationary, that means it is not changing with respect to time. So if it is not changing, then it is function of number of microstates only. It is independent of the time, that means properties are not changing with respect to time. So this is referred to as a equilibrium state. There was a difference between steady state and equilibrium. Steady state means input is equal to output is not changing with respect to time, and equilibrium means everywhere the property value should be same and it should not change with the time. So it is with respect to space and time, the property should not change. So this is a stationary solution where the density is not a function of time, and that is referred to as thermodynamic equilibrium. Thermodynamic equilibrium. So option 4 is correct. Then metropolis algorithm, as I told you, metropolis algorithm, transition probability of a state m of higher probability, the transition probability from a state m of a higher probability state n to a state n of lower probability. So I have higher probability state m and lower probability state n depending on the energy values. We know exponential minus of beta ei. So energy is high, therefore its probability is less. Energy is less, then probability is higher. So ideally this should not happen, right? We should not go to the state which has lower probability. But using the metropolis criteria, we have to sample that also. That is important when we stuck at a particular local minima when we sample the phase space. And there you know that the the probability is given as density of mn, density of higher space divided by density of lower divided by density of. So we are accepting whether to go from higher possible state to lower possible state. It is not with us, we are accepting with some particular probability. If the values of e increases beyond certain value, it is become less and less probable, but then still we are sampling. For example, if the probability is 0.01, that means we are sampling 1 in 100 attempts. So probability is less, but we do sample that point. So this is the probability. Option B is correct. Then the last question, which condition must be satisfied by the shape of the simulation box when using PBC? PBC is what? PBC is periodic boundary condition. To reflect a bigger system, we are allowing the molecules to go from this box to other box, which is imaginary. So this boundary is imaginary boundary. This is an imaginary boundary. This is an imaginary boundary, right? Imaginary boundary where the particle can move from this location to other location and come back, but same has to happen in all the spaces. So what we are doing here, we are assuming the same thing that is happening in each and every state, right? If the particle moves from this location to this location, everywhere it will move. If it crosses two boxes here, and reaches here, every particle will cross two boxes, right? So what is happening? It is a space filling. You cannot have some periodic boundary condition which will look like this, because if it's stuck over here, we don't know how to get out of it. So it should be space filling. It should be space filling among various other options. It should be space filling. So this is about what we have discussed. So I'll just quickly go through what we have covered. So we are going to understand molecular thermodynamics, and there we know we are going from a larger time scale to a smaller time scale, from centimeter to angstrom level scale. And then for that we see how position of the particle and velocity of the particle is changing, that we take track of using something called as phase space. We have to sample. We can sample it by following the time, or we may randomly sample it. The ultimate aim is to sample it correctly. There will be some zone which has to be sampled higher than the zone which is having lesser probability. So there has to be a weighing factor which tells you to how to sample the non the less probable state, that is being given by the formula that we have solved, right? Given by the metropolis algorithm. That's all about it. And then to get the energy, we need some formula that we call to refer to as force field, which is a combination of equation and the parameters that will represent the system properties. If it is a generic one, which is called as physics based model or generic model, where we just say, okay, what is the qualitative trend, what is the predictions, or what is the trend that is there. But if it is specific to a particular system, then it is called as molecular force fields, and that we generally use to have the accurate modeling of the system. And based on that, we have solved some questions. So that's all about this session. So we will meet in the next class, and we will discuss some more aspects of molecular simulations, and we will solve the assignment questions similar to what we did today. So if there are no more questions, we can stop the discussion over here, and let's meet in the next class. Thank you guys. Thank you for connecting. Have a good day.